to allow that to happen?
Okay, the question is about a very remarkable feature of quantum physics, which is that two particles that appear to be quite a long way apart actually interact with each other faster than the speed of light, apparently. It's a very peculiar feature of quantum mechanics, and the query is it related to one of these forces? Well, in principle, it's a feature of quantum mechanics, not of the forces, but the only forces that act over a long distance are electrical and gravity. These short-range, weakened, strong nuclear forces are very, very short range. And secondly, it's not a question of a force. This entanglement is not communicated by a force at all. The particles don't interact directly. Quantum mechanics is extremely subtle and very, very hard to understand. I mean, the mathematics is clear. There is no dispute that it seems to be a correct theory that agrees with experiment. But it's philosophically extremely problematical. And the universe. And my take on this is the universe is extraordinarily subtle, much more clever than we could have thought of. I hope it doesn't answer your question. But,
There's just this feeling that everything is connected somehow. Yeah, no.
I don't think that quantum entanglement has anything specific to say about the values of constants or the strength of forces. It's a feature of particles obeying known forces and known laws.
What's the relationship between the Higgs boson particle and the Higgs boson field? I mean, are they two different things? Yeah.
They're two different things, but very closely related. I am, to some extent, out of my depth here, but I will try. The mathematics at its basic level seems to say that particles like the photon and the gluon and the W and Z bosons that do the Greek force should all have no mass at all. The sort of basic theory would say, no, these ought to be massless particles. It's a bit of a mystery why they have mass. The equations seem to predict they have no mass. It seems very hard to make it consistent if they've got mass. However, the idea of the Higgs field is that it's a field that its lowest energy state is not zero, but has a finite value. In other words, it sort of automatically drops into a state where there is a Higgs field. And when the Higgs field exists, then some particles have mass because they interact with the Higgs field, and some particles don't have mass because they don't interact with the Higgs field. So the Higgs field is the really important thing, which is supposed to explain, for example, the difference between electrical forces and weak forces. Okay? Now, if the Higgs field exists, then the structure is such that it ought to have a particle associated with it, which in fact is related to how strongly curved the Higgs field is. So the Higgs boson is a sort of part of the motion of the Higgs field. If you went to very, very high temperatures, like what we think may have happened just after the Big Bang, it would be so high that the Higgs field would actually aggregate to zero. There wouldn't be a Higgs field. And at those very, very high temperatures, the electrical photons and the weak bosons would all be the same. They'd all have no mass. It would just be one united force. And then as the universe cools, the Higgs field goes down into a finite value, and some particles get mass. That's what they think.
And if the Higgs boson and the Higgs field don't exist, if they find they don't exist, does that ruin the whole standard model?
I think the simple answer is yes. I think the reason that the people in CERN all really more or less believe to a man that the Higgs boson must exist is because they're so convinced that the standard model is right, and the Higgs boson is part of the standard model. No, if it doesn't exist, they'll have to invent something else which does the same job. Okay? And there are theoretical reasons why it shouldn't exist, because the Higgs field should have a huge energy which is enough to blow the universe apart. Okay? We'll talk about the the acceleration of the universe, what's called dark energy. And if the Higgs field exists, it appears to have a dark energy which is approximately, count the millions, a million times too big. Okay? So that's a bit of a problem. The universe ought to be expanding a million times faster than it is, which is quite a big error. But they're not too worried about it, because there's another calculation about different things which say that the universe ought to be expanding a million times too fast. So if you don't worry about that, why worry about a million? No, to be precise, there are serious theoretical reasons why the Higgs field might not exist. And there are some very sort of serious physicists who say, don't really believe in this, but they haven't got another explanation. But I'm out of my depth here, as you probably gather.
How can you prove that the Higgs boson doesn't exist, rather than that your experiments haven't found it yet?
Well, what you can say is, if the Higgs boson exists according to the standard model, there is a very precise prediction of things that should happen. The problem is that you can only work out what should happen if you know what the mass of the Higgs boson is. So what they say is, suppose it's got this mass, then we'll work out the consequences. Suppose it's got this mass, then we'll work out the consequences. Okay, you can work out things which ought to happen. Now, on that basis, they have proved that it cannot happen if it's got an energy of less than 114,000 million electron volts. And it cannot exist if it's got an energy more than 128,000 million electron volts, unless you go to a hugely high energy which has got other problems. So within about the last 6 months, less than that, they've narrowed it down to this very narrow range where if it exists, that's where it's got to be, because if it was in another area, we'd have seen it doing things. Again, this is all if it is a standard model Higgs. Okay? Now, as you probably know, news conference on December the 13th, they think they may have found it at 125,000 million electron volts. But if they found it, the bump that they've seen is only just statistically significant, by not enough to put any money on it. And actually, the bump they've found is about twice as big as the standard model says. So if the standard model is correct, they shouldn't have found it yet. What I think everyone believes is when they start the LHC again in the spring, it's closed down now for the winter, because electricity is too expensive in the winter. So they do other things in the winter. But after the skiing season stops, and they'll start it again, and probably by this time next year, we will know whether it exists or not. By which I mean whether a standard model Higgs, one that fits exactly with the equations, exists, and whether it has so much mass. And I think they can say if it's not between 114 and 128, then it ain't nowhere. And whatever exists must be something different. Is that?
Yeah.
No one else, though, I just wanted to come back on the gentleman who said everything's connected, because I was watching a documentary the other day which said that every electron in the universe, of which there are more than 10 to the power 100, has to be at a different energy level. I'm afraid I really don't know what I'm talking about, but I'm just repeating what I heard, parrot fashion. And so there was a quantum, I think it was a quantum mechanicist, or nuclear physicist, Richard Feynman, and he said that you could pretend, or it could be the case, that every electron in the universe is actually one electron. So, yeah, there is an argument, you could put an argument to say that
Richard Feynman had a model of physics where electrons and positrons were related. An electron was a positron going backwards in time, or more precisely, a positron was an electron going backwards in time. So instead of that huge number, it was one electron going up and down the length of the universe. I think it's a pretty sort of complicated model, and I don't think it's actually related to the entanglement problem. But what you were saying is important, and I never said anything about fermions and bosons and what they were. I think it may be important just to elucidate that in other questions. In an atom, say carbon, you've got 6 electrons, and they're attracted to the proton. What stops them all going zooming down into the proton and just disappearing? Because an electron and a proton attract each other. Well, what stops them is the fact that they're fermions. Fermi particles, you can only have 1 electron per state. You can't have more than 1. And therefore, once you've got 2 electrons in the inner shell, the next 4 have got into the next shell. Do you follow me? So fermions, 1 particle per state. So in carbon, 6 electrons, you put 2 in the bottom state, spin up and spin down, and then the next 4 spin up and spin down into the next state. Okay? Bosons are different. You can get as many bosons as you like in the same state. In fact, they like to be in the same state. A laser, for example, a laser has got lots of photons in it, and they're all in the same state. Millions and millions and millions of them, and that's fine. So the basic difference between bosons and fermions is that fermions, Fermi particles, things like quarks and electrons and neutrinos, they have to have each 1 state each. Bosons, things like gluons and photons and whatnot, they can all pile in to the same state.
But it's interesting then that because then the electrons on one side of the universe must have to know what state the electrons on the other side of the universe are.
Don't think so actually, because there's a carbon atom over there and a carbon atom over there. This has got a state on this nucleus, this has got a state on this nucleus, and they're not interfering with each other.
No, but they have to be at different energy levels. I'm just repeating.
I think what he's saying is a bit confusing, and I don't think that's correct. This carbon atom's got certain energy levels, and you can fill it up with 6 electrons, and this one's got another set. They're the same ones, but they're a different carbon atom.
I've got a question not about particle physics, though about time. Are you able to give an explanation to demonstrate why time slows down for someone travelling near the speed of light? To the observer, that is.
It is very counterintuitive.
Yes.
But let me first of all state what Einstein's theory says. It says that if someone is, say, in a train moving very fast